Hello students, in our last lecture we studied about gravitational potential energy. Now today we are going to start topic number 8.8, escape speed. Now students, we know that when a stone is thrown in the upward direction, what happens? It falls back. Again, if a stone is thrown with some greater speed in the upward direction, it will move up and then once again it falls back to the ground. Again, if the same stone is thrown in the upward direction with some greater speed than the previous one, that will move in the upward direction. Once again it falls. So can it happen that if a stone is thrown in the upward direction with such a speed that it will move out of the gravitational field of the earth? So students, if an object is thrown with such a speed, then it will move out of the range of the earth. Means range means the gravitational force of the earth, and then it will not return back to the earth. And the speed with which it is thrown in the upward direction, that speed is known as escape speed. Now the answer to the question that is it possible that when the object is thrown with such an escape speed, the object will not return back to the earth? So answer to this question is given by the principle of conservation of energy. So now suppose an object of mass m is thrown in upward direction with speed vi. Vi means it is initial speed, and it does not return back to the earth. That is, it has been escaped from the earth. Let the object reaches infinity. Means when it is thrown from the earth, it reaches to the infinite distance out of the gravitational field of the earth or gravitational force of the earth. So it reaches infinity. That is out of the gravitational force of the earth, and that its speed there is vf. Means when it is thrown in the upward direction with some greater speed, what will happen? Gradually it will move out of the gravitational force of the earth. Then when it reaches at the infinite distance, means at the point where no gravitational force of the earth acts, but after that also it might have some velocity. So after infinity it will move with that final velocity in the same direction. So that is vf. It doesn't mean that it will just reach the infinity and it will stop. It will have its kinetic energy because that object is thrown with some greater speed. So after infinity also it will move in the upward direction. But suppose if the stone is thrown with some speed, some minimum speed, so that gradually it moves up, its speed decreases, and exactly at infinity its speed, that is final speed, becomes zero. Even that is possible. So that speed given to the object from the earth can be called a v initial minimum speed. So if with that speed the object is thrown in the upward direction, then it will reach at the infinity and its speed will just become 0 and it is not going to return back to the earth. But if the speed is more than this minimum speed, then what will happen? It will reach the infinity and then still it will move in the upward direction if the speed is more than the minimum value. Now, the total energy of an object at any time is the sum of its kinetic energy and potential energy. Means when the object is on the earth, suppose this is the earth, and if the object is lying here, then we know that it has its potential energy. On the surface of the earth, it has the potential energy. This we have studied in our previous topic, and potential energy is always negative, that also we know. So when the object is simply lying on the surface of the earth, it has its potential energy only. But if the object is thrown in the upward direction with initial velocity vi, then what will happen? It will have its potential energy also, as well as due to velocity it will have its kinetic energy also. And if we add potential energy and kinetic energy, then we get the mechanical energy of this object. Also, when this object is thrown in the upward direction and if it reaches the infinite distance, then once again at this point it will have its potential energy plus kinetic energy. If the object is still moving after infinite distance, then it will have its kinetic energy. And if it is reached at the infinity, means out of the gravitational force of the earth, then at that point its potential energy will be 0. So this thing we are going to apply, but we know that according to law of conservation of energy, energy can neither be created nor be destroyed, and so whatever the total energy was at this point, the same energy will be at this point. So now let us start the process. On the surface of the earth, total mechanical energy initial, I for initial. So mechanical energy of the object on the surface of the earth is its kinetic energy and its potential energy. Now what is kinetic energy? It is half of mvi square, because vi is the initial velocity and m is the mass. So kinetic energy will be this. And on the surface of the earth, its potential energy, gravitational potential energy, is minus gmem upon distance is re, because when the object is on the surface of the earth, from the center of the earth its distance will be radius of the earth. So now let us give this equation number 1. So this is on the surface of the earth. Now suppose the object has moved to infinity. Now at this point, suppose its velocity is vf, that is final velocity. So at this point, that is at infinity, final mechanical energy is given by kf plus uf, that means sum of kinetic energy plus potential energy. Now as it has speed vf, its kinetic energy will be half of mvf square, and its potential energy will be minus gmem upon distance is infinite, so infinity. Earlier the distance was re and the speed was vi. Now the speed is vf and distance is infinite. But anything by infinity is 0. So this term will become 0. So what is remained? Half of mvf square. Let us give this equation number 2. So we obtained final mechanical energy of the object as well as initial mechanical energy of the object. So now comparing these two equations, that is equation number 1 and equation number 2 according to law of conservation of energy. So equating these two, we get half of mvi square minus gmem upon re, that is this, is equal to half of mvf square, that is this. Let us give this equation number 3. Now students, suppose the initial speed vi is such that at infinity the speed of the object just becomes 0. That means final speed becomes 0. In that case, that initial speed with which the object is thrown, that can be called as minimum initial speed. So that when the object reaches at infinity, its final speed just becomes 0. And that minimum speed is nothing but it is an escape speed. So applying this condition in equation number 3, now vi becomes vi minimum, and once again this vi becomes vi minimum, and at that time vf is equal to 0, and if this vf is 0, then this term on the right hand side will be 0, and so we get this equation. Here it is now 0, and in place of vi now it is vi minimum. Now students, simplification you can do on your own. What we have to obtain? We have to obtain the formula for escape speed, which is nothing but it is vi minimum. So we have to just make the subject vi minimum. So now this term is brought towards right hand side, so as it is negative it will become positive. Then mass on both the side cancels out, remain here half of vi minimum square, and here gme upon re. Then this 2 will brought here, so what will remain here now? Vi square minimum, and here it will be 2 gme upon re. Now as this is square of the minimum speed, so taking square root on both the side, we will get here vi minimum and here root of 2 gme upon re. So I hope students you understood this. Let us give this equation number 4. This is the formula for the escape speed. Also students, this formula can be written in terms of small g and re. Here it is in terms of capital G, mass of the earth and radius of the earth. And you can see that this g, me upon re, these are constants only. And if we convert this equation number 4 in terms of this by using this formula, we know that G is equal to GME upon RE square, that we have studied in our second lecture. So if we'll use this concept in equation number 4, then we will get this equation. Here also you can see this small g and RE, they are constants and their values are known to us. So if we put the values of this constant in this equation, then we can get the value of escape speed on the earth. Students, let me show you this. GME upon RE square can be written as small g. So here in this equation, if I multiply RE in numerator and in denominator, then this denominator will be RE square. Is it clear? Multiplying and dividing by RE. So now for this we can write small g. So we can obtain 2 small g RE, and that is this. Now students, putting the values of these constants, we know that value of G is 9.8 meter per second square and radius of the earth is 6400 kilometer. So here when we put these values, we will get escape speed on the earth, that is VE, which is equal to VI minimum, is 11.2 kilometer per second. So students, if we throw a stone with this speed in the upward direction, then it will not return back. But you can see this speed is not a low speed, it is a very high speed. It is in kilometer per second. So it is not possible for us to throw with this speed. Or even if we fire a bullet from the gun in upward direction, then also it will not have this much speed. This is a very large speed. But if we are able to throw an object with this speed, then definitely it will move out of the gravitational field. But still there is an air or atmosphere on the earth. So when we will throw this object with this speed, even it will have the friction with the air, and due to friction it may happen that its speed will decrease gradually and rapidly, so it may not reach to the infinity. But if we neglect the resistance due to atmosphere, then definitely with this speed the object will move out of the gravitational field of the earth. And so I have written here equation 4 and 5 clearly indicates that the escape speed of an object does not depend on its mass. From the formula it is clear that in both this formula there is no small m. Small m means it is mass of the object which is thrown in the upward direction. So it is not dependent on the mass of the object. And so if you want to throw a heavy object in the upward direction to escape from the earth gravitational field, or a small object to escape the earth gravitational field, then the speed given to both should be exactly 11.2 km per second. Hence, if an object is thrown with this speed ve from the earth, it will escape from the gravitational field of the earth forever. Now students, the escape speed for the moon is 2.3 km per second, and if you compare these two speeds, this is for the earth and this is for the moon, then you will find that this speed on the moon is 5 times smaller than that of the earth. So students, as the escape speed for the moon is comparatively low than that of the earth, and this is the reason, or this might be the reason, that the moon has no atmosphere. It is because when the gas molecules are formed on the surface of the moon, which has velocities larger than this, will escape the gravitational pull of the moon, because when the gas molecules they are formed, they might have the speed more than this, and if they will have this speed or more speed, then they will escape the surface of the moon or the gravitational pull of the moon. And so this is one of the reason that the moon does not have atmosphere. Now example number 8.4. Students, here two objects are given, spherical objects are given, their radius is same, but mass of the first object is capital M and the mass of the second object is 4 times of M. Means this sphere is quite denser than this. This is less denser and this is more denser. It is because their volume is same, but here mass is more. So now suppose these are two spheres with their same radius and different masses. Distance between these two spheres from their centers is given 6r, and here we have to find the speed, the minimum speed with which an object is thrown towards second sphere. An object of mass m is to be thrown from the surface of first sphere towards the second sphere so that it can reach to the surface of the second sphere. Students, we know that any object having mass has the gravitational force. So here these are the two masses, so they both have a gravitational pull on each other, as well as they can act the force of gravitation on any object of mass m. So here also, if any object is suppose here, then this object is under the effect of the gravitational force of this second sphere, as well as it is under the effect of the gravitational force of this first sphere. So it is clear that this object will move towards this side due to this sphere, or it can move towards sphere 1 also due to the force acted by this sphere 1. But we know that at this point, if the force acting on this object due to this sphere 2 is more than that due to sphere 1, then the resultant force will be towards second sphere. Or it may happen, if the object is closer to this sphere 1, then the gravitational force by sphere 1 will be more, because here the distance is less, and the gravitational force on this object due to second sphere will be less, as the distance between these two is quite large. So the object can move towards sphere 1 also, but we can get a point where the gravitational force acting on this object at this point N, which is called a null point, where the force acting on that particle due to second sphere will be equal to the force acting on that particle due to first sphere, that is F2 and F1 will be equal at this point. And so if any object is kept at this point, then it will remain stationary, because both the forces F1 and F2, they will cancel each other at this point. The points other than this N, at that point the force will not be 0. Means if I select any point here other than N, then the resultant force will be towards second sphere, and if I select any point here, then the resultant force will be towards sphere 1, but at point N the force will be 0. So let us first apply this concept, that let N is a point at which the two forces cancel each other, that is F1 is equal to F2. Now F1, you know that according to universal law of gravitation, if the object is placed here, then the force acting by first sphere at this much distance, which is denoted by R here, this distance we have taken, so the force will be G into M into small m upon distance square, and so I have written F1 is G capital M into small m upon R square. Similarly, we can obtain F2. Now look at the figure. From this point, this distance from the center of the second sphere, from here to here, this distance is 6r, and this distance is r. So this distance will be 6r minus r. From figure it is clear that the distance of this point N from the center of this second sphere will be 6r minus r. And so F2 is equal to G, mass of second sphere, mass of the object, and distance square. Students, simplification you have to do on your own. I have not shown more steps, but we have to just obtain the relation of this small r which we have taken and capital R. Here you can see in this equation both the side GMM that will cancel. So what is remain here? 1 upon r square on left side, and on right side it is 4 upon 6r minus r square. Now we can take square root on both the side. So taking square root on the both the side, on left side we will simply get 1 upon r, and on right side it will be root of 4 is 2, and root of this will be simply just remove this square. So in the denominator here on right side it will be 6r minus r. And so after this, if you will do one or two more steps, you will find that r small r is equal to twice of capital R. Let us give this equation number 1. Now students, here I have written that as it is sufficient for a particle to reach at point n when it is projected with speed v, thereafter the gravitational pull of second sphere will pull it. Means, what is our aim? In this example, our aim is to just find the minimum speed with which an object is thrown towards the second sphere from the first sphere, so that it can reach to the surface of second sphere. So it is clear that if the object is thrown with the speed v, so that it will reach at point n, just reach at point n. So if we will just reach at point n, then what will happen? After that, this sphere will pull this object towards it. So our aim is to simply obtain the speed with which the object can just reach at point n. After that, the gravitational pull of second sphere will pull it, and the object will reach to the surface of this second sphere. So now, applying that condition, we will use the concept of law of conservation of mechanical energy. So mechanical energy at point A. Remember students, at point A, when the object is thrown with this speed v, this object of mass m will have its kinetic energy as well as its potential energy. As it is having velocity v, the kinetic energy will be half of m v square plus potential energy. This object is on the surface of this sphere 1 when it is thrown. So it will have its potential energy, and we know that potential energy is always negative, and it is g, mass of the sphere capital M, mass of the object small m, and distance between these two objects. Distance between these two objects is this, which is nothing but radius. So it is r. So kinetic energy plus potential energy. So I hope you understood this. So I have written mechanical energy at point A will be kinetic energy at point A and potential energy at point A. But kinetic energy will be half of mv square, and potential energy, as I shown, for the particle at point this, it will have its potential energy due to this sphere which I have shown. Also this particle is in the range of this sphere, So it will have the potential energy due to this second sphere also. And for that, we have to consider this distance. And this distance will be how much? We know that this distance is 6r. And this much distance should be minus. And this is nothing but is r. So 6r minus small r will be 5r. Mass of the second sphere is 4m. Mass of the particle is m. So it is quite simple, students. And so, students, here it is the potential energy due to both sphere 1 and sphere 2. For sphere 1 it is minus g m small m upon r, and for second sphere it is minus g 4m, because the mass of second sphere is 4m. Mass of the object thrown is m and distance is 5r. Now students, after simplification, means you have to simplify this on your own. So it will take one or two steps more to reach from this step to this step, and it is quite simple. So now I am not going to waste such a time, and I left that simplification on you. So you will get this term. This is as it is. Let us give this equation number 2. Now, when the object reaches at point N, the mechanical energy at point N is kinetic energy of the object at point N and potential energy at point N. But students, we have considered that when the object is thrown from the surface of first sphere and when it reaches this point N, its speed becomes 0. Its speed just becomes 0 or nearly equal to 0. After that, this second sphere will pull it and it will reach here. But here at point N, the speed of the particle which is thrown is 0. And that's why here the kinetic energy at point N of that particle of mass m will be 0. Now about potential energy. Once again, the potential energy for an particle at point N will be due to this first sphere also and due to second sphere also. Now, from the center of the first sphere, this point N is at distance r, and from the second sphere, from its center, the distance of point N will be how much? It will be 6r minus r. This distance is 6r, and we want this distance from the second sphere, so it will be 6r minus r. So now it is quite simple, as we have done for this. The same thing we are doing here also. Potential energy is minus g m into small m upon, now the distance is r. Then for second sphere, minus g mass of the second sphere, mass of the particle which is thrown, and distance is 6r minus small r. So I hope you understood this. Once again, simplifying this term, you will get it as minus 3 by 2 g capital M into small m upon capital R. So this simplification is up to you. You have to simplify on your own. And students, you have to, during simplification, you have to put this small r is equal to twice of r, because earlier we have obtained this. So in place of this small r which we have taken, this small r which we have taken, that is to be now kept as 2r, and then you have to simplify it. So you will get the energy at point N is equal to minus 3 by 2 G capital M into small m upon R. Let us give this equation number 3. But students, we know that the energy at point N as well as at point A will be same according to law of conservation of energy. So EA is equal to EN. So comparing equation number 3 and equation number 2, we will get this equation of V. So once again students, simply you have to put EA and EN from equation number 2 and 3, and then you have to simplify yourself and just make the subject V, means you have to obtain the equation in terms of V, and you will get V equal to root of, see, power is 1 by 2, so power is 1 by 2 means it is root of 3 by 5 Gm upon R. Now students, as I left simplification up to you, and it is normal simplification, normal mathematics is used, but still if you don't find this simplification easy, or if you are not getting this answer, then you can ask me.